and welcome to our new lecture series. Today we have discussed about the atomic structure of the material. Let us start our new topic, atomic structure of the metal. First of all what is the mean by engineering material? Where it is used? The knowledge of material and their properties is great important for a design engineer. A design engineer must familiar with the effect which the manufacturing process and the heat treatment have been the properties of the material. The engineering material mainly classify into two categories. It may be metal and non-metal. The metal may be classified into two categories. It may be a ferrous materials and it may be a non-ferrous materials. The ferrous material are those which have the iron as the main constituent, such as a cast iron, wrought iron and steel. The non-ferrous material are those which have a metal other than iron as the main constituent. Then it is the copper, aluminium, brass, tin, zinc. These are the all example of non-ferrous materials. First of all, which are the content are included in this topic? So atomic structure and atomic bonding in a solid, crystal structure as well as crystalline and non-crystalline materials, Miller indices, anisotropy, elasticity, elastic behavior of the composite materials, structure and properties of the polymer, structure and properties of the ceramic. Now discuss about the atomic structure. Atomic structure is defined as the atom consists of a small nucleus composed of a proton and neutron, which is energized by a moving electron in their orbits specific energy level. The topmost orbit electron valence electron affect the most material property that are the interest of engineer, like chemical property, nature of bonding, size of the atom, optical, magnetic property, electrical property. These are the some example of that. Now electrons and protons are the negative and positive charge of the same magnitude, being 1.60 into 10 raised to minus 90 coulomb. Neutrons are electrically neutral, but the proton and neutron have approximately the mass. The mass may be 1.67 into 10 raised to minus 27 kg, which is larger than the of an electron weight. That means 9.11 into 10 raised to minus 31 kg. The atomic structure may be a atomic number, that means the number of the proton per atom. Atomic mass, that means defined as the sum of the masses of proton and neutron within the nucleus. The atomic mass is measured in atomic unit, that means AMU unit, where AMU is 1 by 12, the mass of the most common isotope of the carbon atom, measured in grams. A equal to Z plus N, where N is the number of neutrons. What do you mean by isotope? Isotope is an atom with the same atomic number but different atomic masses. A mole is the amount of matter that has a mass in a gram equal to the atomic mass in AMU of the atom. Thus, a mole of a carbon has a 12 gram per kg. The atomic structure of that material, the number of atom or molecule in a mole of a substance is called a Avogadro number. That means Ny. We have to define Ny equal to 1 gram divided by 1 mu. We have to define those values is 6.023 into 10 raised to 23. Calculation of that number, maybe you have to define number n equal to NAV divided by m, where m is the atomic mass in AMU. Thus the graphite of carbon with a density are given, mass is given, so you can easily find out the number. Most of the solid material we have atomic density in order to 6 into 10 raised to 22. That's about 39 million atom per centimeter. Mean distance between the atom is a 0.25 nanometer. It is give an idea about the scale of atomic structure in a solid. Atomic bonding in a solid. There are two questions arise during the material engineering when we have to find out the structure. The bond are two kinds. It may be primary, it may be secondary type. Primary bond, it may be a relatively stronger, exist in almost all solid material like ionic, covalent and metallic bonds. These all are primary bonds. Secondary bond, that means a relatively weaker bonds, exist in many substances like water along a primary bond. Hydrogen and van der Waals are the secondary bonds example. The atomic bonds in a solid may be classified into two categories, primary and secondary. Primary may be ionic, covalent and metallic. Secondary may be a fluctuating, included polar induced and permanent induced. Primary interatomic bond. These bonds are invariably involve valence electrons. The nature of bond depend upon the electronic arrangement in a respective atom. Atom tend to acquire a stable electron arrangement in their valence orbit by transferring this or sharing the electron or proton or valence electron in leads to formation of the bond. The bond energies are 1 kg 1000 per mole. Ionic bond is defined as it is also called a primary bond that exists between the two atoms when transfer of electron result in one of atom to become a negative and one is a positive. That means the interaction of both the atom that will be create a ionic bond. That means this bond is a direct conflict of a strong Coulomb attraction between a charged atom. Basically, ionic bonds are non-directional in nature. The real solid ionic bonding is usually exists along the covalent bonding, like NaCl is a one type of example of ionic bond. Covalent bond is also a primary type of bond. This bond comes to exist when the valence of electrons are shared between a pair of atoms, thus acquire stability by structuring the valence configuration. Covalent bonds are stereoscopic. That means each bond is between a specific pair of atoms which where a pair of electron is opposite to each other. Typically, covalent bonds are very strong and directionally in nature, like a H2 molecule is the example of a covalent bond. Metallic bond. A metallic bond is also a primary type of bond. This bond comes is to exist when if electrons are shared between a number of atoms. That means the arranged positive nucleus are surrounded by electron pool. A shared electron are not specific to a pair of atoms in contrast to covalent bond. That means electron are delocalized. That means not in a proper manner are arranged in a crystalline structure. As a shared electron are delocalized, a metallic bond are a non-directional bond. Very characteristic property of metal like high thermal and electrical conductivity are the result of presence of delocalized electron pool. A secondary interatomic bonds are defined as the bond involve atomic or molecular dipoles are involved during a metallic structure. The bond can exist between induced and permanent dipoles. That means the bond come into exist because of a Coulombic attraction between the positive end of the dipole and negative end of the other dipole. The bond are energized in the order of 10 kg per mole. The secondary interatomic bond also existence of these depend upon the three kinds of the dipole: fluctuating dipoles, polar molecule dipoles, and permanent dipole. This dipole may be defined those structure may be crystalline or it may be a non-crystalline. The perfect dipole bonds are also called a hydrogen bond. As a covalent bond, we have to know this bond are bonded hydrogen. For example, CH, OH, FH are said single electron of that particular bonds. Those strong electron attractive force with the negative end of the adjective molecule. Hydrogen bond in a responsible for the water exist in a liquid state at the room temperature. Crystal structure. What do you mean by crystalline structure? Those structures have a solid matter are made of atom or molecule which are arranged in a specific manner. That means it may be on a perfect manner will be have to arrange. That's called a crystalline structure. Otherwise is a non-crystalline structure. Group of atom or specific arrange is called a crystal structure. Lattice is used to represent a three-dimensional periodic arrangement of that point coinciding with the atom position. Unit cell. What do you mean by unit cell? Unit cell is a smallest repeatable entity that can be used to completely represent a crystal structure. It is a building of a block of a crystal structure. Structure of solid we have to define. All solid substances are either amorphous solid, that means it may be a crystalline or it may be a non-crystalline structure. Crystalline structure, that means arranged in a perfect manner. Non-crystalline structure may be it non in a perfect manner. All solid metal have a iron, copper, aluminum. Those matter are a crystalline solid. The definite order, manner and form of atom producing a geometric shape or aggregate, that's it is called a space lies or crystal lattice. A crystal is a composed of unit cell. A unit cell is defined as the contents of smallest number of atoms which when taken together have all the properties of the crystal of the particular metal. The unit cell are arranged like a building block in a crystal. That means they have the same orientation and the similar faces are parallel. A unit cell may also be the defined as the smallest parallels which could be transposed in the three coordination direction to build the space lattice. Those space lattice are various substances in a different sizes and shape of their unit cell. So unit cell may be characterized by the type of atom, or that means the radius, cell dimension, what is the meaning of A and C, number of atom per unit cell, what is the coordination number, what is the atomic packing factor. The most of these parameters are directly affect to the unit cell. So common crystalline structure have the crystal structure maybe you have to see in this table. The simple cubic structure have a atomic number is the n equal to 1, where coordination number is a 6, atomic radius is a 4 divided by root 4, and atomic packing factor is a 0.52, where in a BCC n is a number 2, coordination number is 8, the radius is a 4 divided by root 3, and atomic packing factor is a 0.68. Phase FCC phase center cubics is a n is a 4, cn is a 12, and coordination number, that means the radius is a 4 by root 2, where is a 0.74, and hexagonal is a 6, 12 and 74. That means the efficiency of that common crystal structure is a higher in a FCC as well as in a hexagonal, lower in a simple cubic structure. So we have to discuss one by one those all structure they are affect on a crystalline or non-crystalline structure. First one is a body crystal structure, or this may be defined as a space lattice in a unit cell of a body center cubic space lattice. There are 9 atoms and the 8 atoms are located at the corner of the cube and 1 atom at the center of the body. This type of lattice found in alpha ion like a tungsten, chromium, magnesium, molybdenum, titanium and barium and vanadium. FCC will be find out in the space lattice in a unit cell of FCC. There are 14 atoms, the 8 atom at the corner and remaining 6 atom at the faces of the cube. This type of lattice is found in a gamma ion, also in aluminum, copper, lead, silver, nickel, gold, platinum and calcium. And the last one is a CPH, that means a close packed hexagonal. This space lattice in a unit cell of a close packed hexagonal space lattice, there are 70 atoms. The 12 atoms are located at the tail corner of the hexagonal prism, 1 atom at the center of the 2 hexagonal faces, and 3 atoms are the symmetrically arranged in the body of the cell. This type of lattice is found in the magnesium, cobalt and cadmium, antimony, bismuth, beryllium, titanium and zirconium. So these are the some crystal structure of the metals. Now we have to discuss the Miller indices. What do you mean by Miller indices? A system of notation is required to identify a particular direction or plane. That means the formulas involving Miller indices are very similar to related to formulas for analytical geometry, simple to use. Use of reciprocal avoid to completion to infinite geometry. Specifying dimension unit cell terms means that the same label can be applied to any plane with the similar stacking pattern and regard the crystal class of the crystal. The plane is always 111 step to same away regular of the crystal system. Miller indices direction may be defined in x, y and z. A vector coordinate length is placed parallel to the required direction. The length of the vector projection on each of the three axes are measured in terms of unit cell dimension. These three numbers are made to smallest intervalues known as indices by multiplying or dividing by a common factor. The three indices are enclosed u, v and w. That means you have to take on also x, y or z. Also, what do you mean by Miller indices plane? Those plane define a unit cell of dimension if a plane is passing through a origin where it is needed to construct a parallel plane to original plane. That means you have to construct xy plane, yx plane and yz plane. Take a reciprocal of this, interpret number, clear fraction as well as reduce the set of smallest integer to these three indices enclosed in a parenthesis HKL. You have to define also x dash, y dash or z dash number. You have to see in a figure a Miller indices example. The direction may be x, y and z. So direction is 0, 0, 1, second direction is 0, 1, 1 and a third direction is a 1, 1, 1. You have to take on a first of all 1, then double 1 and 3, 1. Plane ACG is a 101, plane OAGB is a 001. So you have to indicate those number on x, y and z. So you have to particular indicate, first of all you have to define the direction and then the plane. Miller indices, where it is used. What is the use of Miller indices? If you have to define a plane parallel to the axis, it's interpret it infinite and Miller index will be a 0. Never alter the negative number. This implies the symmetry that the crystal may be not have user bar over the number of represent that negative number. A planar or direction or family is not necessary to parallel to other plane or the direction of the same family. The smaller the Miller indices may be nearly parallel to the plane or to the axis or vice versa. Multiplying or dividing by Miller indexes by a constant, then you have to define that plane. Also we have to define integrate use in Miller indices contain more than one digit. That means the indicate must be separated by the 3, 10 and 13. The useful convention may be used if you have to use the x, y, z or x dash, y dash, z dash. If you define x, y and z, all you have to use u and w. Then u equal to h, v equal to k and w equal to h. So Miller indices is a 1, 1, 1. If a parallel, then you have to multiplication and summation hu plus kv plus lw will be a 0. If a two plane, then hk and l, that means h2, k2 and l2. So h1 into h2 plus k1 into k2 plus l1 into l2 will be a 0. If a two direction, then u1, v1, w1, u2, v2 and w1. If you have to find out those values, so u1 into u2 plus v1 into v2 plus w1 into w2 will be a 0. If you find out the distance between them, then you have to find out those atomic number, divide by root s square plus k square plus l square, and between them angle you have to find out. Then cos theta equal to h1 into h2 plus k1 into k2 plus l1 into l2 divided by h1 square plus k1 square plus l1 square into h2 square plus k2 square plus l2 square. Due to with that equation you have to find out that distance as well as angle. The Miller indices that indicate that the describe of all possible solution or plane of direction in the crystal. It may be a indices are based on a 4 axis, 3 axis, 3 plane, 2 axis plane at 120 degree apart. Fourth axis is perpendicular the place plane. Then you have to find out the extra index, then t equal to minus u plus v into and I equal to minus h plus k. So base plane is a 0, 0, 1 and prismatic plane is a 10 and 10. Polymer, what do you mean by polymer? Polymer are made of a basic units called mers. Those are usually hydrocarbon where a major constitute atom are hydrocarbon and carbon. When a structure consists of only one mer, it is a monomer. If more than one, it is called a polymer. Isomer, it is refined molecule those contain the same number of monomers. then it will be a isomer. Like a butane and isobutane is the example of isomer. When the polymer has one kind of merge in its structure, it is called a hypopolymer. Polymer made with the more than one kind of merge, it is called a copolymer. Polymer structure may be a linear, branch and cross-link structure. Linear, that means a unit are joined together end to end. In branch structure, where side to side are joined together, and in a cross-link structure where chains are joined one to another at the various position by covalent bond. This cross-linking is usually achieved at the elevated temperature by the additive atom. That means the vacuolization of the rubber is an example of cross-link structure. Network may be defined a transfactual mud unit in a 3D network comes under the category of exopics, phenol, formaldehyde. These are the examples some of a polymer structure. It may be linear. You have to see in a figure branch structure, cross-link structure, network structure. These are the example of polymer structure. There are two type of plastic will be used in materials. There are two type of plastic. The plastic are the synthetic material which are molded into a shape under the pressure, which or without the application of it. This can be cast, rolled or extruded or laminated and machine. Following are the two types of plastic is there is a thermoplastic and a thermosetting plastic. The thermoplastic setting plastic are those formed into under shape, heat and pressure are the result in a permanently hard product. The heat first one soften the material, but the additional heat and the pressure is applied. It become hard by chemical change known as the phenol formaldehyde bakelite is an example of thermosetting plastic. In a thermoplastic do not become hard with the application of heat and pressure and do not chemical change during the occur. They remain soft at the elevated temperature until they are hardened by a cooling. This can be remelted repeatedly by use successive application of heat. Some of the common thermoplastic are PVC, polyvinyl chloride is the example of a thermoplastic. A basic difference between a thermoplastic and thermosetting plastic is that in a thermoplastic you have to remolded that materials. In a thermosetting plastic you have not remolded that material. Polymer mechanical response at elevated temperature is strongly depend upon that chain configuration. Based on the chain configuration, we have to discuss thermosetting and thermoplastic material. Polymer crystalline, the crystallinity of a polymer is more complex than the metal. If you have find out the crystalline on the polymer, that range from almost crystalline to the atmosphere in a nature. It depends about the cooling path on a chain configuration. Crystalline polymer are more denser than amorphous polymer. Many crystalline or semi-crystalline polymer from this semi-sulfuric or sulfuric. Each sulfuric consists of a collection of a ribbon like a chain folded laminar crystalline like a PVC is an example. You have to see in a diagram those it may be where it is rigid, where it may be rubbery and where it is viscous. When we have to increase that temperature at this time it may be a rigid, or may have to decrease it may be a viscous form. Ceramic are inorganic and non-metallic material. Atomic bond in a ceramic are mixed with the covalent bond as well as ionic bond. The proportion of the bond is specific for the ceramic. Ionic bond exists between alkaline or non-alkaline metal and oxygen and halogen. Mostly oxide, carbides and nitrides of the metal are the ceramic, like a sand, glass, bricks, marble are the example of the ceramic. The ceramic structure may be a building criteria for the structure maintain neutrality, collecting, packing. The packing efficiency can be characterized by coordination number, which can be depend upon the onion radius ratio, that means RC by RA. Those ratio may be less than 0.0152 to greater 1.000. That means this can be vary according to that coordination number. You have to see that coordination number and atomic radius also you have to see. For the atomic contamination ratio is a 0.015 to 0.225. At this time coordination number is a 3. 0.2 to 5 to 0.141, then 4 0.141 to 0.732. At this time coordination number is a 6. 0.732 to 1.00. At this time coordination number is a 8, and greater than 1 is a 12 coordination number. These are the ionic arrangement of a coordination number. You have to see here in a figure coordination number is a 3, where atom is a 1 in a center. Coordination is a 4, where atom is in a center. Coordination number is a 6, those is a hexagonal type. Here you have to see the rectangular type, where coordination number is a 8. Ceramic crystal structure. The ceramic crystal structure may be classified according to that direction of that particular motion. The AX type, most of the common ceramic, they have to assume different structure of a variety coordination number. Like a rock stall structure, the coordination number is a 6, like a NaCl FeO is the example. Calcium chloride structure, where coordination number is 8, like a CSCl is the example. Zinc blended structure, where coordination number is 4, is a zinc chloride. Silicon chloride is the example of the structure that, where XM and XP type number of atom are contained a different unit cell is mode of a unit cube. That means M is not equal to a P. Those atomic structure or atomic performing factor are not equal, then you have to example. At this time CaFeO, THO2 are the example. When the ceramic contain more than one kind of the content cation, also called a peroxide crystal structure, is a BaTiO3. Silicate. Those silicate are most common ceramic in nature. Silicate as a constituent element, silicon and oxygen are the most abundant in the earth crust. Bond between Si and O2 is a weak ionic, very strong covalent in nature. Thus the basic structure of that silicon is the SiO4 tetrahedronium. You have to see in a figure. Those atoms are arranged at the corner of the structure and one in a nature of center of the body. The center of the body is a silicon and the corner of the body is a oxygen. Silicate also is a oxygen atom, and corner of the tetrahedron is said by adjustment tetrahedron. Silica can be both crystalline quartz and glass. Crystalline form of silica are composed and comparatively open, thus the low of density compared with the amorphous glasses. The addition of network modifier NO2 and intermediates are lower melting point, thus the melting point are most effective, as well as the carbon percentage is are also more effective. That means you have to see an iron carbon atom, the higher temperature the metal will be in a liquidous form. At the some lower temp, if you have to decrease the for 1400 to 932 degrees Celsius, at this time it may be in a liquidous or it may be in a solidus form. But at the lower temperature 732 degree or lower, it may be a for a solidus form. That means at this time ferrite will be a normal, but strength of that material will be also lesser. You have to see on an iron carbon diagram. In a complicated silicate, corner oxygen is shared by other tetrahedride, thus the content is the Si4, SiO2O7, Si3O9. The oxygen content may be a different, so you have to the content will be different. Carbon is not a ceramic but a allotropic form of a diamond. Is a diamond is a Cc covalent bond, the highest non-hardness. The hardness is higher in a diamond. Semiconductor, this will be used in a semiconductor for high thermal conductivity, metastable. These are some characteristic of the diamond. Graphite is another allotropic form of the carbon. Is a layer structure. When we have to use a layer structure, at this time a hexagonal bonding within the planar. The layer of a good electrical conductor is a solid lubricant. Another allotropic form is a C60, also called a fullerene, bulky ball. The structure of reassembled hollow ball may be a 20 hexagonal and 12 pentagon, where no pentagon, two pentagons share a common edge. So fullerenes are the compared to a diamond, graphite will be higher. Fullerene and related nanotube are a very strong, ductile, could be one of the important future engineering materials. The imperfection in a solid, there are so many defects will be arise during the imperfection of the solid. It may be a line defect or it may be a point defect. The imperfection in a ceramic of point defect and impurities, their formation is strongly affected by a change the nuclearity. The Franken defect is also called vacancy defect, and Schottky defect is one type of vacation and nation vacancy. The impurities are introduction of impurity atom in the lattice is likely in the condition where the charge is maintained. That means the electronegative impurity that substitute lattice and the atom are electropositive substitutional impurities. The mechanical response of that ceramic is the ceramic of a limited because of the presence of microscopic flow generated during the cooling stage of a processing. However, the ceramic are high with hardness. Ceramic are a good structure material under the compressive load. The plastic deformation of a crystalline ceramic is limited by a strong interatomic forces. Little plastic stain is accomplished by a process of a slip. Non-crystalline ceramic deformed by a viscous flow. The characteristic parameter of viscous flow may be a viscosity. Viscosity decrease with the increasing temperature. However, at a room temperature, viscosity of a non-crystalline or crystalline structure may be different. The mechanical response may be important for the crystalline. That means hardness, one of the best mechanical property of the ceramic, which is utilized in many applications such as abrasive grinding media. Hardest material is are known as a ceramic. Ceramic having a no hardness about 1000 or greater are used for the abrasive characteristic. Grip may be used for a ceramic